Please welcome Steve Chien to Google.
Thank you very much, Boris. So I'm going to be talking today about some work that was done with the European Space Agency. I want to emphasize this was all collaborative work with ESA. At the top of my team is, the top list here is my team, including myself, Greg Rabideau, Danny Tran, Martina Trosch, and Josh Doubleday. The rest of those lines are actually all ESA collaborators of mine. The operations engineers, Federico Nespoli, Miguel Perez Aycar, Mark Costasita, as well as liaison scientists, Claire Vallat, Bernard Geiger, Nico Altabelli, and the software team, Manuel Fernandez, Fran Vallejo, Rafi Andres, and Michael Kuppers. So I have to emphasize very strongly this has been a collaborative effort. So I'm going to start off by talking a little bit about comets and why we're interested in comets and why we want to go there. So I'm going to start with a video here, and this video is actually very good because it's technically accurate. It's quite unusual.
When the Rosetta spacecraft set off for a rendezvous and landing on the distant comet 67P Churyumov-Gerasimenko.
One thing here to remember is compare the pictures of the comet here that are in this PR video, which is before we got there, to what they actually turned out to be like.
Comets are really important. They're like a time capsule back to our past. They were formed just as the planets were formed in solar system formation.
So this is actually accurate with the planetary disk, the formation of the solar system.
We'd like to understand then, is that the original material that the solar system kind of went from something like that to water and oceans and palm trees and the like? How do we know what our original solar system was made out of? Does the comet really represent some of that original material? And it's so very different. How do we get, from there to where we are now?
So actually, there were a few things that were probably in that video that were a little too fast going by. But early on, before the solar system really existed, between 4 and 4.5 billion years ago, there was just a ball of gas, dust, ice, and so on. And because of conservation of angular momentum, it begins to form into a disk. And that disk, the elements in that disk are what are called planetesimals and cometesimals. And so as they come together and they collide and they hit, they stick together. And so generally, very slowly, everything forms, and eventually it becomes the planets that we know. And the problem is, if we look at, on Earth, the different materials we have, they're too distorted, they're too evolved and mature from a solar system formation standpoint. So what happens is when we look at the things on Earth, they've been affected by water, they've been affected by the sun. So they're not like the solar system was 4.5 billion years ago. Comets are actually, they enable us to look back into what the solar system was like over 4 billion years ago. And the way we do that is we have to go and find these comets. And the comets exist in two main areas, the Kuiper belt and the Oort cloud. So the Kuiper belt you might know about because Pluto is no longer a planet. It's just one of many, many Kuiper belt objects. So that's the primary near source of comets. And then the Oort cloud, I didn't know this before I started working on Rosetta, is much further out. It's so far out, it's about 1/4 of the way to the nearest star. So it's really what some people might consider interstellar space. And ideally what we'd like to do is we'd like to go out into the Oort cloud and take one of those objects and study it. But shockingly, going 1/4 of the way to the nearest star is kind of hard. So that would take a long time and a lot more money. Let's suppose the next best thing you want to do. You want to find one of those objects that's coming into the inner solar system. So those of you who remember your physics would know that if you have something that's in as eccentric of an orbit as that, its angular momentum is going to be conserved. What does that mean? When it comes in, it's going to be going really, really fast. Okay? The other problem is its period might be hundreds of thousands of years. So you need to find this dark object, which is 1 light year away. You need to predict that it's going to come in. And you need to predict this, by the way, about 15 years in advance, because that's how long it takes to build the spacecraft and plan the trajectory to meet it. So kind of hard things to do. OK, so now what's the next thing we're going to try and do? We're going to try and get a Kuiper belt object. Well, it turns out that there's what are called Jupiter main belt comets. These are comets that were in the Kuiper belt, and they were perturbed at some various point in time. And so they're sort of in the orbit of Jupiter. That's kind of good, but Jupiter is kind of hard to get to also, right? Churyumov-Gerasimenko, which is the target that we had for Rosetta, is actually a main belt comet. And the extremely impressive nav people figured out that about in the 1800s, about 1850, it was perturbed from a 10-year orbit to a 6-year orbit. And then from that time period, it was perturbed again in 1950 to an even shallower orbit. And since that time, it's been coming into the Earth. Okay? And so, well, coming in near the Earth. Coming into the Earth would be a very bad thing for all of us. So we have this comet that's only 50, 60 years been coming in and having all of these volatiles burnt off of it. So this is a great target for us to get to visit. So, well, originally it was, so the question was, what was the path before? So originally it's a main belt comet, then it was perturbed to have a roughly 1 decade orbit that still did not take it close enough to the sun. And then it was perturbed into this 6-year orbit, and I think I actually messed up the dates, around 1950. And then since then, it's actually been in this 6-year orbit. And since its period is 6.6 years, you can do the math and figure out how many times it's had the volatiles disturbed. Does that answer your question? OK, great. Still, it's quite hard to get to this comet. And why? Because when it's in this highly eccentric orbit, it's going really fast relative to the Earth. So Rosetta actually launched in 2004. And we had Mars, Earth, Earth, Earth. Okay? So we've been flying over a decade to try and catch this comet. And you said, wait, you told me the comet only has a period of 6.6 years. Yes, that's right. We've been flying so long to match with this comet, we missed it the first time around, and we're catching it the second time around. And this is actually entirely accurate here. We chased it from behind to arrive at the comet way far out there. That outer line is, in fact, Jupiter. So now you can look at Jupiter versus an Earth orbit. And then we followed it through perihelion, which was August 2015. And so this is really a fantastic chance to visit this comet because we chased it, we caught up with it, entered orbit in August 2014. We saw it through the closest approach. And then an additional year, we saw it cool down and become less active. So just to put this in a little bit of scale, in 2004, when Rosetta launched, this was your cell phone. Does anybody here have a flip phone still? OK. The top pop artist was Britney Spears. And this last one went over quite well at Harvard. Some undergraduate started a company in his dorm room called The Facebook, and we'll just leave it at that. OK. So Rosetta is really one of the most challenging space missions ever conducted. So 6 billion kilometer cruise for over 10 years, as we talked about, and all of the 4 gravity assists. 2.5-year hibernation. So originally, they had a different target. They actually had a launch vehicle problem, and they had to adjust to this target. So for 2.5 years, the spacecraft actually was existing just on heaters and batteries and a timer and thermal points to wake it up. Went out to 5.3 AU, and AU is, of course, the distance of Earth to the sun, so about 93 million miles. I'm an American, so I'm not so good at the metric correction. Rendezvous with a 4-kilometer object traveling at 135,000 kilometers per hour. And then this slide is actually a little out of date. So normally we only went about 10 kilometers, but since last week I can say we went to 0 kilometers since the orbiter actually landed on the comet. But before that we flew flybys of about 2 kilometers. Orbiting a changing comet environment, and I'll tell a little bit of a story about how the spacecraft safed one time when we flew too closely. An unknown landing environment, we'll talk more about that later, and orbiting a low-gravity body. Just to give you an idea of the scale of the Rosetta mission, 26 instruments on both the lander and orbiter. Over 2,000 people worked on the project. And of course, the only thing that we can really relate to is the total cost, about $1.7 billion US dollars. That figure obviously changes with exchange rates. So NASA was quite thrilled to be part of this ESA mission. I have to always emphasize it's an ESA mission. And specifically, Rosetta is really the truest sense of space exploration. And I'll talk a little bit about some of the things that we learned about comets that if you'd polled all the cometary scientists before, they would have all been 180 degrees in the opposite direction before. So recall earlier in the video, I showed you this round, mostly spherical object. The actual comet turned out to be a contact binary. So we can see it here. That information was actually scooped inadvertently. Basically, the terminology, there's two sets of terminology for the geography on Churyumov-Gerasimenko. There's the Egyptian Rosetta theme. And then there's, of course, everybody sees this and says this is a rubber duck. And so there's the head, the body, the neck, the head lobe, and the body lobe. And people will often refer to that even in the science team meetings, even in papers and stuff like that, particularly when you're talking about the landing. If you're curious, there's actually publicly available 3D models. The highest resolution model is not publicly available. It's 90 million facets. It's based on OSIRIS data. But like the Matthias model is publicly available. And if you're curious, you can print it yourself. So what happened is that there's two pieces, cometesimals as they're called, and they came together at just the right velocity, and they stuck. Originally, when we first got near the comet, people thought that, well, no, maybe the stuff in the neck is more volatile, and it ablated off as we came closer to the sun, as we kept coming closer to the sun. But now, based on the analysis of composition, they believe it's in fact a contact binary. Early on, one of the scientists believed that, in fact, there were 5 different pieces that came together based on a texture theory. But there are many different opinions, and that's the beauty of science. This gives you some insight into just how textured the comet is. So there's all these features, there's boulders and so on. And now MSL has made this quite common, but at this point in time, the Chiva selfie off of the Philae lander camera was actually quite unusual. They only realized they could actually, in fact, do this as they were checking out the Philae lander. And then, believe it or not, it's remarkably hard to actually get the comet in the background. I'm very bad at selfies, so I empathize with the ops team. So in November 2014, we delivered the lander. This is actually from the OSIRIS camera showing the lander dropping away. And remember now, see how stationary the lander is, right? It's not tumbling. That's because it has flywheels on it to keep it from tumbling, okay? Well, what happened when we actually deployed the lander? Well, as the lander mission manager likes to say, we landed not once, but 3 times, okay? So if you look at this imagery, it's quite fascinating. You can see this is actually an image sequence that was designed to actually search for the lander. And so they bracketed the estimated landing time. And you can actually see here, I'm going to just hoof it over here a little bit. These images are about 5 minutes apart. This one's really interesting because you have the touchdown point before and after. And those slight pock marks are the actual footprints of the lander. And here's the one where it's like, if you saw this in real time, stop. It's hopped and it's going away, okay? And just so you don't think that the second part of my talk is all made up, this is the actual plan that came off of my laptop. And that's actually showing those OSIRIS imaging sequences in that plan as they were planned, okay? So what actually happened in the Philae landing? What happened is the lander hit, and it turns out that the comet was several orders of magnitude harder than they expected. So there are several mechanisms that are designed to allow the Philae lander to secure itself to the nucleus. First of all, it has legs that flex, okay? So that should absorb some of the energy. Second of all, there are screws, 3 screws, 1 in each of the feet at the end of the legs, that at contact, they try and screw in. But the primary securing mechanism is there are two harpoons in the body of the lander that when the contact is detected, they fire, and those are supposed to secure the lander. Unfortunately, what happened is the screws did not secure it, the harpoons did not fire, and so the Philae lander bounced. And to make things worse, the flight software on the Philae lander said, okay, I have these flywheels, they're eating up power, I've now landed, I'm going to turn them off to save energy. And that's entirely planned, okay? So now what happens is the Philae lander is tumbling, right? Because, of course, it didn't hit perfectly flat. And it actually tumbles for over an hour. And so the problem here is you're landing on the head. The original intended landing site is about here. And I forgot to mention, the comet is rotating. And it's rotating at between 12 hours. I think at this time it was about 12 hours and 40 minutes. But the rotational period of the comet has varied from 1220 to 1250. As it comes into the sun, it changes actually. And so it basically bounced for over an hour. So think of this as you're trying to land in Mountain View. You hit, and you bounce, and you end up landing somewhere around Las Vegas. Okay? No, actually probably further, 1/12 of a circumference, right? Then we got very lucky. The next bounce, we hit a very soft spot. So after that, it's only about 7 minutes, okay? And then eventually we landed. And then now we'll talk about where we actually landed. So first, an eye test. Quick. Oh yeah, go ahead.
The second bounce, what did it land on its feet?
Okay, so the question is, the second bounce, did we land on our feet? Because we know we landed on our feet for the first bounce, because that's what everything was designed for. It is believed that roughly we landed on our feet, because otherwise there would have been a lot of damage to the lander, but we don't actually know. We have very little information.
Since you didn't know the shape of the comet ahead of time, how was the landing spot determined? Did you get images back and then pick it out yourself?
Very good question, yeah. So we did not know the shape of the comet before we arrived. All that we had was very, very grainy photogrammetry, which is like basically albedo information. So when you see these repeated lightnings and darkenings, you can infer something about the shape. And that's mainly from Hubble. But when we exited hibernation in January 2014, we actually entered a very close orbit to the comet in August 2014. And we did not deploy the lander until November 2014. So we were frantically mapping the comet, primarily with OSIRIS and VERTIS, the two of the main imaging instruments, in order to choose a landing spot. There were 10 landing spots that were proposed. And then there was a long and heated discussion about exactly where to land, because the scientists say, wow, like the neck looks really interesting to me because it's got these, weathered terrain. And the engineers say, what, are you insane? That's like the worst place to land. If you're off by a little bit, you're floating in there and the comet goes like that and kind of like smashes you. And then the scientists also would like to be in particular areas of illumination and non-illumination, and there's a particular sweet spot. Not too hot, kind of like the Goldilocks thing, not too hot but not too cold, right? You want enough sun to power yourself, but not too much sun that you bake the lander. So there was a long is 4 weeks, a very well thought out process to choose the landing site. And then of course we ended up landing somewhere else.
What relative velocities are we talking about between the lander and the comet? And then
very good question. So actually, the relative flyby velocities that we have on a Rosetta are extremely low for a space mission. So when we actually fly by the comet, so we generally, if that's the sun and this is the comet, the spacecraft flies on the sunward side, and there are a few reasons for that. One is there are two tails that the comet has. One is the debris tail, which is in the anti-delta V direction, and then there's the ion tail, which faces away from the sun, right? That's actually what people see, right? They see the ion tail. You want to stay away from the ion tail because, all these charged particles hitting your spacecraft is kind of not cool. You also want to stay on the bright side of the spacecraft because all these imaging devices over here, they're not really seeing much, right? So they're not going to want to be over there. So the gravity is so low that we sort of like fly like a skateboarder, or used to fly like a skateboarder. I keep getting the tense wrong. So we would fly these line segments like this with the cameras pointed at the comet, okay? Now, then the lander itself, the intended velocity is actually 1 to a fraction of a meter per second. And then actually when the spacecraft landed, when the orbiter landed, again, we're talking trying to get it around less than a meter per second. So you're talking like a walking pace, which is very, very unusual for space flight. Yes?
So during the airtime after the bounce, was there any attitude control from the control system, or was it just kind of idling, just waiting for it?
There is no attitude control system on the lander. So that's why you need the flywheels. Yeah.
But it didn't turn the flywheels.
Okay, so now you guys, there's the punchline on this slide. So the test is, who can find the lander? And by the way, think tens of thousands of these images, and then poor people on the OSIRIS team like Ceciliana were actually poring over these for more than a year. It's kind of, this was the best one I had. It actually would have been better if I cheated and given you one without the lander in it. We have one more.
On the shadow area on the right side, below that, what is that? Yes.
Oddly enough, I have one that actually calls it out, right? So then you can see it. Here's the body of the lander. Here are the legs. And it's sideways in a crevasse, exactly as predicted. I say predicted because they use the telemetry data from the solar panels to know the orientation of the lander, right? They know the approximate region. They know they can infer the orientation. For some Earth orbiting CubeSats, like the IPEX CubeSat that I was a PI for, you actually build a tumble model from the periodic current data from the solar panels.
So you mentioned the comet itself is about 4 kilometers in guess diameter or
right.
some equivalent of that. And then the orbiter was orbiting at a distance of about 10 kilometers?
It depends. During the highest activity, we'd have to be closer to 30 kilometers, 30 to 50 kilometers.
Okay.
During the end of mission, some of the flybys, in fact, that's why they were able to find the lander. Okay. Some of the flybys were several kilometers.
Okay, so I guess my question is, does the gravitational influence of the comet extend that far beyond its
well, it
its
extends
surface?
everywhere, right? It's just GMM over r squared, right? It's just a question of how much. And so basically, as the comet is more active, the atmospheric gas, the coma, pushing you away from it is much more than the gravity. So you're really not orbiting it. That's why we were flying those line segments. Okay. So this is actually, the end of mission was last week. That's the last OSIRIS image. It's blurry. Why is it blurry? Because it's only taken at a distance of 20 meters. Nobody designed the camera to take an image that close. It's actually designed for more like a kilometer or more. There's the ALICE last spectra. That's one of the US instruments from Alan Stern and Sweary. And then at the right, it's actually showing the loss of signal from the spacecraft. So we have no hope that the spacecraft is going to come back. Why did they choose to fly it into the comet? There's 2 reasons. One is it's going to die anyway, and you can't leave it next to the comet, right? Because it's not going to end up, by the time it comes around again, it's not going to be next to the comet. There's just no way. The other thing is that enabled them to capture all kinds of unique data, particularly for the in situ instruments, by going in that close. A lot of the heavier species of molecules, they don't actually get to sample them further out.
Did it perturb the orbit?
No, because even though the comet Churyumov-Gerasimenko is extremely, the opposite of dense, porous, yeah, it's still 4 kilometers long, right? Whereas the Rosetta spacecraft is 2 meters, right? So we're talking quite a difference in scale, right? Also, the impact velocity is very low. So some of the major science discoveries from Rosetta, there's a lot of theories about the source of Earth's water. And some of those theories involve cometary bombardment periods. And it turns out you can fingerprint the source of water by the ratio of the heavy to light water isotopes that you see. And so this basically shows the graph of all the different bodies that we've been able to sample from. And you have to take some of these with a grain of salt because they're remote sensing measurements. Rosetta is very good, and it has an in situ measurement of these isotopal ratios, so it's inclined to be much more accurate. But the fingerprint of the ratio is different, as you see up here at the top, it's far above the blue line, which is Earth's ratio. So that tells you that either it was comets from the Kuiper Belt and something else mixing, or something happened to the water afterward, which is really hard. It's really hard to change these isotopes. If you're familiar with like the production of nuclear weapons and stuff, you know, that's like one of these things. It's very hard to do. So this is very strong evidence that at least Kuiper Belt objects are not the primary source of Earth's water. Another surprise was Churyumov-Gerasimenko is not magnetized. So many theories of solar system formation had magnetism playing a major role. There's really not much to change the magnetism of this object, you know, after that period. So since it's not magnetized, that's evidence, strong evidence against the fact that early solar system formation was heavily driven by that. All these plumes and beautiful pictures of plumes that we see, the original mechanism that they thought that those plumes and that outgassing happened turned out to be wrong. So they thought that photons hit, it heats up, and you see these jets, and you see these plumes. Makes sense. Turns out that's not what happens. What happens is the photons hit the water and CO2 ice. They liberate electrons by a process called photoionization, and those ionized particles then cause a subsequent reaction that involves sublimation of those molecules directly from basically solid to gas form. Okay? So this is another one of the major science discoveries from Rosetta. Another one is the detection of molecular oxygen at a comet. Nobody thought that this would be the case. In fact, you could argue this is the most surprising discovery. And again, this is from the Rosina instrument, an in situ instrument. So it's a very reliable find. Another fascinating discovery is COSMA, another one of the in situ instruments, actually has detected organic molecules. Okay? So a lot of people think that amino acids, organics, came from comets, these long carbon chains. This is very strong evidence for that. Another one of the real surprises is all of the pits that we see on the comet. And some of these are quite deep, like hundreds of meters deep. And it turns out what happens is, as the comet heats up and this photoionization and everything happens, it's actually happening, some of it subsurface. So the CO2 and H2O is being liberated subsurface and escaping through this extremely porous comet, and then you have basically a collapse underneath it after too much is liberated, and that's why you see these pits. Okay? So again, these are all things, these are the reasons why we wanted to go to the comet, because we learn all these new things. There's a lot of other things that I don't have fun graphics about. The Philae lander, Kozak and Ptolemy, 2 instruments on it, discovered complex carbon chains as well. Rosina detected glycine, which is an amino acid. This is an in situ detection of an amino acid at an extraterrestrial body. That's an amazing discovery. Okay? And there's many, many more. If you're curious, there's a link there that actually has, if you Google it, you can probably find it as well. There's actually, before the end of mission, they had a series of survey talks on some of the major science discoveries. Okay? So that's the fun background part. And now I'm going to talk a little bit about the AI part. Okay? So first, I have to start out with a disclaimer. So there are many, many elements of Rosetta mission ops. There's Rosetta, then there's the science planning, then of that, there's uplink and downlink. Then within the uplink, there's planning. And then within that, there's 3 phases of mission planning. I'm going to be talking about the middle phase of mission planning because that's where we use the different AI tools. By the way, these bars are obviously not to scale. Okay, so I got asked so many questions about this that I did a controlled experiment. So I got asked, what is Rosetta science planning like? And I used to just say there were a lot of phases. And I tried to be, since I got all these questions, I tried to be more precise. So what I did is I went to my email box and I did a search on Rosetta on this particular day, on the 20th of January, 2015. And at this point in time, all these different planning phases were going on. So at that point in time, we were planning the trajectory for July to October of 2015. So we were in what's called LTP. Then the next LTP, which was March to June of 2015, was in what's called SK, which is we were taking that trajectory and figuring out what campaigns we're going to work on that for what measurement campaigns were going to work and what were not going to work. But in a fairly abstract sense, okay? Like literally taking the observation campaigns from the measurement catalog and seeing the ones that were going to be problematic. Then the next phase is called MTP. That's medium-term planning. And then we're planning at the activity or observation level. So the AI was used mostly in what's called the SK in the MTP phase to rapidly iterate among the different alternative measurement strategies then. After that, the planning goes into a manual planning tool called MAPS, where they drive it down to what's called the sequence level, where those are the actual low-level commands that get radiated to the spacecraft. And then those are actually delivered in weekly or 3- and 4-day bundles. And then, by the way, a lot of these same people were at the same time frantically analyzing all the data before that they'd gotten. There were like 2 different special issues of Science and Nature that came out even during the. That's when you realize, that you're on a mission that has, high science impact. When in November, when we were deploying the lander, we heard that there was going to be a special issue of Science coming out in January, and it's like, in theory, the primary science mission doesn't start until November. So what are we saying here about how much science has already been done? So this is actually one of the medium-term plans. This is one of the most complicated ones that we had. It has about 2,000 observations. Very importantly, it has 2,000 different pointings and slews of the spacecraft. So a slew is when we change from one pointing of the spacecraft to the other. There are about 60 active science campaigns for this month. And there's also all of the DSN, so all of the ground communication stations, the uplinks and the downlinks are also in that. So we have to track that and actually develop that plan very rapidly. In reality, there's a frenzied 1 week where we really take that plan from what's called SK into MTP. And after that, it's very, very hard to substantively change it. So why is it hard to build this plan? Well, the number one reason for Rosetta is because of geometry. I mentioned that we have the spacecraft, and we're flying around like this. Well, the exact viewing geometry that we have really is going to impact the kind of measurement you can take. And so in remote sensing, we have what's called this target observer illumination geometry. So the illumination is the sun. So let's assume it's back there, these lights. The target is someplace on the nucleus. Let's just assume that for now. And so if I'm here or here, it's going to look very different. If I'm looking for plumes, I want a phase angle of, let's say, 130 to 150 degrees. That means I want to be looking at the comet backlit. So all the images of plumes that you see, the comet is all black. Okay? If I'm looking at the surface, I want the illumination behind me, right? But there's a slight problem. Turns out the plus Z deck is where the camera is and the imaging instruments are. The minus Z deck is where the fuel tank is. We don't like the fuel tank to get hot for obvious reasons. So we can't literally go over what's called the subsolar point. That's why we fly in these different line segments, but very rarely go straight across. Okay? And by the way, this comet is rotating at the same time. The spacecraft is flying its trajectory, so you need to be able to identify all of the correct geometries. And so we actually compute all of those, extract them, and that's really what we're searching in. We are searching in time, but we have to extract all of the appropriate geometry. So we actually reason about all these constraints, all of those vectors, all the combinations of those vectors. If there's a vector and there's an angle, probably some scientist is interested in it. And this is an example of our planning around MTP-9, which is the lander delivery. And this is an actual observation where Fabrizio, who's the Virtus PI, says we want to image with a phase angle of greater than 80 degrees, but be within 15 kilometers of the nucleus. And the interesting thing is, those are the different times that we can do that. And then maybe it'll get scheduled there. And he said, well, how come this time didn't get scheduled? And those are the kinds of questions that we have to answer in the different scheduling process. Okay? The pointing can actually get quite complicated. That Alice spectra that I talked about, that instrument is actually a slit. So that red part indicates the slit. In this particular observation, they want to take scans across the nucleus. And this is an observation that's very near and dear to my heart because there's a very similar instrument called UVIS on Europa. And we want to do these scans across the Europa moon when we fly in. And we want to scan for fresh plumes that, again, we can detect spectrally. And then if we find a fresh plume, we want to target that observation on that flyby without the ground in the loop. Why do we want to do this? If you have a plume and you don't catch it until the next time the spacecraft comes around, which for Europa is probably 30 days, those complex organics from that subsurface ocean, they may already be broken down from the harsh radiation environment. Okay? So that your chance of detecting life or the precursors to life there depends on being able to do that quickly. So in this case, we want to do these different scans up and down, and we have to combine this with all kinds of other problems. Like, we don't know exactly where the spacecraft is, so there's some pointing error. So you actually have to scan past the edge of the nucleus. And these get quite complicated. This is actually showing a Moreau scan, which looks like Alice. So we're sweeping up and down here, and then it's going to stop in the middle. And there it stops, and then it goes on. Why did that happen? Why did it stop? Well, it turns out this is a combination, a merger of two different instrument observations. OSIRIS wanted to take a picture of the nucleus. So what we did is we have to plan it so you take this picture of the nucleus, and then the scan happens to be at that point. Okay? And that's how you try and operate the spacecraft more quickly. So the pointing is very, very important. I already mentioned that you have to deal with other geometric constraints like the fuel tank. You also can't point the instruments too close to the sun. That's not a good thing. And then there are different pointing trade-offs. So as we're flying around, the spacecraft is designed so that it goes sideways with the solar panels cutting through the gas while the imaging instruments are pointed at the nucleus. And by the way, all those in situ instruments, where all those science and nature papers came from, they're pointed in what's called the RAM direction, the delta V direction. So everybody's happy until some imaging scientist says, if I'm in close and I look out, I can measure the gas cloud very precisely. So they like that, but then all the in situ instrument people said, what? You're screwing with my data. You're totally messing with my data. So what do we have to do? We have to measure how much of the gas cloud, how many particles are going to be hitting the detectors at various points in time. And for some of the instruments, they need a background signal. So you don't get any data for the first 15 minutes after you slew. So the short story here is you really don't want to point away, the Z-deck away from nadir when you're near. And then how far off you point and how close you are how close to the nucleus you are when you point, those are trades. So we did a series of trade studies on how much science we would be losing of each type. And so that's one of the advantages of having the automated planning system. You can do all these trade studies very easily. You also have to optimize different kinds of pointings. If I'm sitting here and the sun is back there and I'm looking at the nucleus, and I have what's called an inertial target. That's a target that's not moving with the comet. So let's suppose it's a guide star. It's in the corner there, in the corner of the room there. If I'm on this side of the comet and I slew over there, it's a very small slew. If I'm on this side of the comet and I slew over there, it's almost 180 degrees, right? Because we have 30-meter solar panels on the Rosetta spacecraft, it's not very agile. That 180-degree slew would take you over 20 minutes. So we have to actually group the different inertial targets when they are shorter distances, okay? And then there's this other problem. We have a gimbaled antenna. If we slew too quickly, that gimbaled antenna can no longer point at Earth. And we are downlinking data all the time. And that's because we don't have a lot of power, so our data rate's not that high. So all these pointing things really, really flow into the planning problem. Another thing is we have structured observations. So this is an example of one of the most complicated structured observations. All those beautiful pictures and 3D models that you see of the comet Churyumov-Gerasimenko, those are from OSIRIS maps. So what do? They use the rotation of the nucleus, and then they stripe up and down it longitudinally. Okay? And so that's how you construct a map of the entire nucleus. What does that mean? That means over 12 or 13 hours, you want a series of images, and each image will take a certain amount of time. That's exactly what's being scheduled here. But note that the spacing is not perfect because there are different operations constraints where you can't get the spacecraft. So to an AI person, I would say this is a multi-objective optimization problem. These are all of the different science concerns that Holger Sierks, who would be the OSIRIS PI, would bring up. He would say, well, in this month, I asked for 3 groupings, 3 of these mappings, but really, can I have 4? And by the way, I want those evenly spaced throughout that month. Oh, in all of those groupings, I want all 12 images. If you give me 10 of them, then that's not as good of an overall schedule. And within that grouping, they were all supposed to be evenly spaced, right? Then there's this other fun thing. They navigate the spacecraft twice per week, every fourth and third day, alternatingly. Oddly enough, right after they navigate the spacecraft, they know better where it is. When they know better where the spacecraft is, that means your pointing error is lower. Shockingly, everybody wants to observe when the pointing error is lower, right? And then the distance to target is also changing. As I mentioned, as you fly by, you fly these line segments, you get closer and you get further away. There's an optimal distance to target, and furthermore, you don't want variation in the distance to target across these groupings. The local time is changing as the nucleus rotates. So basically, when you get off cadence, the local time of your stripes will now change. That's not good for their mapping. And then the emission angle changes in addition because we're not just staying at the equator, because as we go north and south, that emission angle is now changing. So the way I would phrase this is, it's a multi-objective optimization problem. And by the way, we don't have the objective function. And the scientists will just tell you when you're wrong until they change their mind, right? So there's actually researchers who are interested in formulating this actually as one of these oracle-based objective, trying to infer the objective function. So there's some interesting work going on there. By the way, the scientists also have to interleave all of this with all kinds of engineering activities. So the navigation of the spacecraft, firing of the thrusters, and so on. So in that previous example for OSIRIS, and this is a different example for ALICE, we can't have the ALICE covers open within 30 minutes of a thruster firing because that would contaminate the instrument. So that's an example of an engineering constraint. And then arguably one of the most complicated constraints is downlink management. So as we acquire all of this data, it's filling these buffers. There's 14 to 18 of them, depending on how you count the engineering buffers. And we stream the data into them, and we have to downlink it without overflowing it. Otherwise, you just lost that data that you worked so hard to get. And so that's actually a very hard problem, particularly when we're doing these mapping campaigns. We actually have to empty the buffers. Then we frantically downlink massively. We get all these downlinks to downlink that data as we're acquiring it. And still, by the way, at the end, as you can see here, we're completely full, right? So this is actually one of the major areas of automation here. Okay, so where is the AI scheduling? Well, it turns out all those constraints that I talked about pretty much are modeled in ASPEN, and we have to actually track them and enforce them, okay? So there are all these science constraints, there's all these health constraints of the spacecraft, and some of them are hard constraints. And then some of them are soft constraints. Generally speaking, we attempt to satisfy the soft constraints, but we don't, unfortunately, do this multi-objective optimization. Maybe the next mission. And then how do we search? We actually take the constraints and we break them into two parts. The first part are relatively static. We solve them, and then we use that as a guide to solving the dynamic constraints. And then that's where we really have to do the heavy-duty search. What are the static constraints? Well, once we have the trajectory, most of those geometric constraints are now static, right? Because the geometry, the relative geometry of the spacecraft and the nucleus, it's not changing, or at least if it is, you're not able to know that it's going to change. However, some of the other things are dynamic. The resources are dynamic because when you place a few observations, they're consuming resources that the other observations would need. What else is dynamic? Some of the geometry, like where you're pointing and seeing how long the fuel tank has been in the sun. So we actually take all of the static parts of the problem, we extract them, then we search and solve that problem, and then we use that as a guide for the dynamic search. Okay? And what does this really look like? This looks like what we have at the bottom here. We have a set of observations. We look for gaps in the schedule, usually in pointing, and then we try and insert the observations in places where they satisfy the constraint. And so this is actually showing what that really looks like. These green intervals here are the different constraints. There's about 25 of them that we modeled, different feasibility windows. And then this is literally an animation of the search as it's trying the different combinations of the groupings. And if your eyesight is really good, you can see that these are, in fact, the solutions that the schedulers come up with, at least for now. So this is basically what I said. We take a satisficing temporal solution. We take all the static constraints. We compile them in their temporal constraint network form. We take that and we search in that for all the dynamic constraints. we actually compute all of the validity intervals, all those green and white constraint intervals. In theory, you only have to winnow them down, but we compute them all. Why do we do that? Because the scientist will always come back to us and say, why didn't my observation get scheduled here? And so you have to go and say, well, here are the 4 constraints that you told me, and this is how they're violated in that particular point. The downlink scheduling we actually enforce after we schedule the observations. And that's because there are other triggers that the scheduler is not allowed to pull, but the operations team can pull to say, oh, those 8-bit images, those are now 4-bit images in order to make the schedule work. And then finally, originally when we deployed the scheduler, there was squeaky wheel optimization around this whole loop. What does that mean? That means you take the highest priority observations that didn't get in, you increment their priority, and you try again. As we got into operations, what ended up happening is the operations engineer became that optimization loop, okay? Because it was faster for the people who are very smart to tweak the priorities and try and get whatever result that would, to the best of their knowledge, that the scientists would be happy with. The second part of the scheduling, the downlink management, this is just a different blow up of it. And you can see there are these different buffers that are being tracked. And so the scientists and the engineers would actually take the solution that we would find in our heuristic search, and then in some cases they might try and tweak it. But actually fairly rarely, because it's actually a very hard problem to solve. At the MTP level, you can think of it as a 300 variable, mostly linear programming problem. What are examples of the plan sizes we looked at? I already kind of gave you some examples of this. They're on the ballpark of 2,000 observations. Those would expand out into tens of thousands of constraints that have to be checked. One of the most significant contributions we've made to the mission is during the lander delivery phase, we had to manage multiple contingencies. And then the engineering team was changing what they were going to do in order to correct the navigation and so on. So at one point in time in there, we had 3 different contingencies times another 2 contingencies of land or abort. And we would take what's called a PTSL, which is the engineering plan, and we had to turn it around within hours. So they would completely change the engineering plan, and we would have to redo the science plan around it in about an hour. How did all of this work out? It worked out quite well. Before we actually got to the Comet, we did 2 sets of deliveries of science plans for about 8 months. Each one covered about 8 months. And this was used to assess the different science campaigns, how feasible they were to operate on the orbiter. And significant changes had to be made from this. There were 2 campaigns that it turned out of the 350 or so science campaigns that in the original form would have taken 3/7 of the free observation time of the entire mission. So obviously that's not going to happen, so they had to be redesigned. The Rosetta spacecraft woke up in January 2014. ASPEN was used in this, as I said, this midterm activity planning into the escort phase, including multiple contingencies until about spring of 2015. And so a total of about 28 MTPs were delivered using ASPEN. However, what happened in the spring of 2015 is the spacecraft was flying too close to the nucleus, and the dust cloud blinded the star trackers. It actually was a very dangerous event. It took them 3 days to regain control of the spacecraft. We easily could have lost the spacecraft then. So based on that, they decided they would no longer have a pre-planned deliberative trajectory like 6 months in advance, even with the 2 contingencies. And instead, what they decided is there would be a notional trajectory, and they would just try and fly as close to the comet as possible. And so what that meant is a lot of the pre-planning and optimization that ASPEN was involved in was no longer possible. And so they actually took the constraints that were implemented in ASPEN and basically forced them into the preceding and following phase, in other words, in the maps, and then actually the LTP, believe it or not, it's an Excel spreadsheet where they enforce the constraints. And so that was the planning process they went on with for the remainder of the mission, which is a little more than a year. The data management system, DALEC, is continued to be used and actually was used until the end of mission. So that part was still automated scheduling. So let me just finish up here. What's next? Well, we would like to take these same technologies and put them on board the spacecraft. This is actually a video that we used that's showing a simulation that actually uses Rosetta data, and it shows a smart flyby. So instead of pre-planning out these campaigns, what we'd like to do is take a whole bunch of OSIRIS images and look for plumes. And those are the large boxes. And the yellow line that you see is not a laser where we're shooting the nucleus. It's in fact showing a small field of view instrument like Miro that's imaging the base of a plume that's been discovered in the large imagery. And here you can see the flyby is so fast that the spacecraft can't actually keep the nucleus in view. Why would we like to do something like this? Because right now we don't have any narrow field of view imagery of those specific point targets. Why? Because it's a narrow field of view instrument, what are the chances you're going to actually get the base of the plume? There are other things you'd like to do, like trace the edge of the plume. All of those things are possible if you have the onboard autonomy. And just so you don't think that this is completely made up, these are actually some of the initial algorithms that we have showing the ability to track the plumes, actually track them across frames. And actually tracking them across frames is a very powerful technique because the plumes actually persist over time. There's similar techniques where we want to do this in an Earth-observing autonomous system where you would have to retask just within minutes. And then the most exciting thing lately is what's called ocean worlds. We now believe that there are underneath large ice caps, ocean worlds at Europa, Enceladus, Triton, and even Pluto. Okay? And these are some of the primary locations where we might find extant life in our solar system. And that's because we have liquid, we have energy sources, we have gradients, or we believe we have all of those. So we'd like to go to Europa, melt our way or burn our way through the ice cap, deploy a submersible. We don't know what this underwater ocean looks like, but we know if we have a submersible, it will have a NASA logo on it, evidently. And then this is a little bit inaccurate. So because the scientists would say, oh, let's go look at that water-ice boundary. The engineers would say, pointy, sharp object, right? So more likely you would sample from a plume from a hydrothermal vent because this is one of the most likely sources of life. In fact, there's a guy on my team right now who's on a German icebreaker, the Polar Stern, at 85 North, investigating what's called the Jurassic Massif, which is an Arctic hydrothermal vent where they're searching for new life forms right there. And then, just if that wasn't exciting enough for you, the ultimate challenge is an interstellar mission. You'd have like a 50 or 60-year cruise to go to the closest star. When you go there, the one-way light time is 4.5 years, so you're probably not joysticking that spacecraft. It's pretty much autonomous. The submersible I talked about would have to be autonomous for, let's say, 10, 20, 30 days. This is 80 years of autonomy. So for going wormholes or something like that, this is how it's got to be. JPL has a long line of AI-based autonomous systems. We're very proud of them. I was actually reviewing this talk just yesterday night, and that's when I had to change the Rosetta from the yellow font to the white font, which means it's no longer operational. But we're very proud that a lot of these spacecraft, we are the operational system used to command them. We have flight software on board, both MSL and MER now. We have the software that schedules the deep space network called the communications antennas. So AI is very much alive and well at JPL and NASA. So just to summarize here, I hope you've all come away with the understanding that for a complex mission like Rosetta, the scheduling of the mission is very hard. That's behind the scenes to enable the science. There's a lot of different constraints, and a lot of constraints that are articulated, hard engineering constraints, as well as ones that are not articulated. They're competing science campaigns. Most of the constraints are soft. A typical planning process for one of these missions would be very interactive and incremental. What are the implications for AI research? Well, first of all, we can take heart that AI is being used in such a big mission like this. But to me, the lessons are a lot of these basics of AI that maybe aren't so sexy anymore, but they're considered, like in your first or second AI course, you already learn about them. Constraint enforcement, constraint propagation, heuristic search. These are all important for schedule generation, but almost more importantly, problem analysis, observation campaign, and constraint analysis. And in this particular use case, the scheduler is not automating everything. It's amplifying the human's ability to explore more alternatives, explore more of the schedule search space. And one thing I would say that's very important here is it's actually, in these cases, it's more important to be able to understand what the scheduler did than maybe a 0.5% better solution. So just different acknowledgments. I always have to start off with acknowledging my wife because she allowed me to work on this project. It was a 3-year project that turned out to be a 5-year project, and project with no operations that turned out to have a lot of operations, including 1 week a month in Madrid for the primary phase pre-lander delivery. So I have to thank my wife for still being with me through all this. ASPEN is a joint NASA, JPL, ESA effort. I have to acknowledge all the wonderful collaborators that we've had at ESA, and some of them we're working with even now on the JUICE mission. We have to acknowledge the larger team and, of course, our technology sponsors. And finally, tragically, last year, we lost our US Rosetta Project scientist, Claudia Alexander. And in memory to her, I always note this as in all my talks. She was very, very influential in science. She's also the former Galileo project manager and very much a STEM advocate and role model for women in science, and should be commended and remembered. With that, thank you all for your attention.
You mentioned not having this objective function for what you're doing. Is that mainly because it's such a difficult problem space, or is that also a difficulty in assigning relative weights or merits to different science tasks?
I would say yes to both of them. So it's also the nature of the mission is very interdisciplinary, and there are so many diverse instruments. So we have specific problems, particularly NASA, that we do know the objective function. So for example, if you're mapping the planet, then there are some measures of coverage that you can assess, and there's a quantitative. So it's more like, if you're scheduling a production line, you know what your quality metrics are. You want to produce as many widgets as possible. But still, even that's quite complicated. There's a mission called NISAR, which is an interferometric synthetic aperture radar mission that's jointly between JPL, NASA, and the Indian Space Agency. And so they have these different coverage metrics, but it turns out there's about 50 different science campaigns, and each one has its own coverage metric. And so one is monitoring glaciers, another is looking at earthquake faults, and another. And so when you look at the combination of all of them, well, then it's not quite so clear what your objective function is. But there, I think you have a fighting chance. On a mission like Rosetta, it's too interdisciplinary. Certain things just have to be negotiated. So really, you have to look at it as in what we call an IA problem, intelligence amplification, not really a completely automated problem.
So you mentioned several times flying in line segments. So I was curious about that and why, it seems like flying in curves around it would be more fuel efficient.
Except you're you're optimizing for a lot of things, and fuel efficiency would be one of them. But you're also flying the segment that's the easiest to navigate. So by navigate, we mean predict, control, and estimate. And so when Rosetta is a chemical spacecraft, so it's not like ion propulsion. So it's not firing its engines continuously. So with the line segments, you basically get to the end, you orient, and you fire. And then you do a correction burn, and then you don't fire until the other end of the line segment. So flying a continuous curve might be better for some reasons, including viewing geometry, but it would be a lot more stress on the navigators.
Thanks.
So also, you'd have to be very careful because, as I said, they try and fly to slice the solar panels through the coma, particularly when we were at perihelion in August 2015. So doing that exactly would be exciting, let's say, because it would depend on the accuracy of your coma model, because you'd be continuously varying the delta V direction. So I would say that I'm not disagreeing with anything you're saying, but there are a lot of constraints there. Oh?
The interstellar mission. Imagine a software that runs that autonomously. What would be the major modules or building blocks of something like that?
Wow. Okay, really putting me on the spot here. I'm not sure we know. There are advocates who say, well, okay, that has to be some kind of very general evolving, spacecraft, evolving software and whatever. I don't know how you guys feel here at Google, but at least for me, I'm like, yeah, not quite yet there and comfortable with that. Because we're talking about, like many trillions of dollars, probably to conduct such a mission like that. So you want to have quite a bit of confidence that it's going to work. So I would focus more on traditional software. But really the question is, when you get there, you have so many open choices. What do the planets look like? Which planets do you go see first? Knowing full well that when you enter orbit around one planet, do you have enough resources to then go visit another planet? Well, really to look at it in context, you got to orbit it. Flying by is, just enough to get you really curious, right? So to make an analogy to Rosetta, the reason why there are all these misconceptions about comets is they've flown by. They call this the golden era of comet missions because depending on how you count, there's been half a dozen to maybe even 10 comet missions. But those are all flybys of like a day or two. This was 2 years at this comet. Completely different ballgame. So when you get to this other solar system, to me, I would set the bar low. I would say the smart software has to just do better than the dumb software alternative. So it has to pick a planet, get into orbit around it, map it, search for signs of life, look for different biosignatures. But there's even quite a bit of controversy about what those signs of life would be, right? I mean, I'd welcome any inputs from any of you guys. If you got to a planet, you knew nothing about it, what would you look for? It's a really hard question.
So does any of the AI software have trace its heritage back to the remote agent?
I would say not directly, but certainly the remote agent was the first time that we were able to fly a planner. I would say the fact that there's a planner and exec on board is similar. So it's still in this generic view of like a 3-layer architecture. But the individual things have changed a lot. So the planning that we use is much more incremental planning and not batch planning. And then when we talk about flight software, which is a more direct comparison to remote agent, because remote agent was flight software, not ground software, I would say the main differences are that we now emphasize being very close to the science. So a very big part of that timeline that I showed you is that we have all kinds of image processing software, clustering software, very detailed instrument analysis software for spectral unmixing, if you guys are familiar with remote sensing. So it's figuring out the constituencies of the individual elements that you're looking at from the spectral lines. All those things are now very much what we do.
Please join me in thanking Steve for visiting us at Google.